Dear student, warm welcome to NPTEL Phase 2 program video course on geosynthetics engineering in theory and practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. The name of the course Geosynthetics Engineering in Theory and Practice. This module number 1, lecture number 4, Introduction to Reinforced Earth.
Now, I will talk about the recap of the previous lecture, what so far we have covered. We have covered the anisotropic cohesion concept, and we have covered laboratory central Pons-Strauss's cohesion theory, Coulomb's analysis, New South Wales cohesion theory, and failure by rupture of the reinforcement, failure by slippage of the reinforcement, and composite failure envelope, basic design of reinforced soil wall, Coulomb's force method, and Rankine force method. So, from this lecture we have learned the failure and analysis of the reinforced soil wall and how the structure fell, reinforcement fell. Reinforcement may fail due to the slippage, or reinforcement may fail due to the rupture. Therefore, one has to take care that proper kind of the selection of the reinforcing element, in order that it can prevent the slippage as well as the rupture. Now, I will discuss some standard analysis of reinforced earth. This is the current reinforced earth system analysis, the internal stability. Now, we should know what is critical slip surface. Critical slip surface can be defined the locus of the point of maximum tensile force in the reinforcement is called as the maximum tensile force line. For example, that this is the soil wall with inextensible reinforcement. There are two types of the reinforcement. One reinforcement is the inextensible reinforcement. That means it is a metallic strip. So, it is inextensible reinforcement. So, failure mechanism or the locus of the critical slip failure is different from the extensible reinforcement. If we consider extensible reinforcement, we can say the geogrid or any polymer material is a extensible reinforcement. So, failure envelope for the extensible reinforcement also different from the failure envelope or inextensible reinforcement. So, in this lecture we want to show you that what will be the failure envelope in case of inextensible reinforcement and in case of extensible reinforcement. and what is the locus of the point. You can see here this is the reinforcement material, and the tensile force is maximum here, T maximum. The locus of this point for this reinforcement. Similarly, you can see for this reinforcement, this is the maximum tensile force little bit away from the facing element, and this locus of the slip point is here. Like this, for this maximum, this is. Now, if you can join, you can see join this point, then you can have a biplanar failure surface. So, when the soil wall with inextensible reinforcement, that is metallic reinforcement, this failure is biplanar failure surface. And if h is the height of the reinforced wall, then this distance will be equal to 0.3 times of the height of the wall. Now, this biplanar failure surface has divided into the two parts. This is active zone and this is restraining zone. So, you can see that how the shear stresses moves toward the facing element, and whereas shear stresses is moved away of the facing element. So, in the active zone, it lies between the facing element and the maximum tensile force line, and the shear stress on the reinforcement acts toward the facing of the oil. This means the soil transfers the tensile load to the reinforcement. In case of the resistance zone, it lies behind the maximum tensile force line. You can see this is the maximum tensile force line and is lies behind the maximum reinforced soil line. And the shear stress on the reinforcement act away from the facing element. Shear stress is acting away from the facing element, and reinforcement set tensile load into the soil. So, this process of load transfer are the fundamental mechanism of reinforced soil. So, this I already explained that when the soil wall with inextensible reinforcement, and this is a biplanar failure surface, but what will happen in case of the extensible reinforcement? We will follow up also for the next what will be the failure pattern for the extensible soil reinforcement. Also, we will check up that if there is a surcharge load, or if there is a slope on the top of the wall. For example, that if we consider this is as a reinforced soil wall, and also if you consider this some surcharge load is here, also if there is a some angle which you call the beta. So, what will be the change of the coefficient of active earth pressure? We can show you. So, for this slope angle, you can calculate the what will be the coefficient of active earth pressure when there will be no surcharge load, and what will be the coefficient of active earth pressure when what will be the coefficient when this angle is equal to the beta. Now, if it is a extensible reinforcement, that means if it is a polymer material, you can see here that the failure zone is the linear, it is the linear zone, and this is the zone of maximum stress, or it is the potential failure surface. same, this is the active zone, this is the restraint zone, and this is the reinforcement, and this making at an angle of 45 degree plus pi r by 2. And here also the shear stress is acting through what the facing element in the active zone, and in the restraint zone the shear stress is away from the facing element. So, you can draw a linear line of failure line. So, it is the Rankine line, and if the h is the height of the reinforcement, so this will be equal to h tan 45 degree minus pi r by 2. So, you can look at here, this is the total length of the reinforcement, and this is the LE which we call the maiden length or bond length, and this active zone is equal to L of R. So, you can calculate this L of E by the pull out test, and then you know that what will be the total length of the reinforcement in, and then you can calculate the what will be the length of in the active zone. Now, we will discuss the maximum tensile force in the reinforcement layer. Recent research reported that the maximum tensile force is primarily related to the type of the reinforcement, modulus, stiffness of the reinforcement, extensibility, and the density of the reinforcement. In case of inextensible reinforcement, the coefficient of lateral pressure decreases linearly from the top of the wall to the value of the active earth pressure coefficient KAR at a depth 6 meter and remain constant. You look at this figure, that how this lateral pressure is decreasing with the depth, and it remains constant when it reaches to the 6 meter. That means, in case of the metallic reinforcement, this value is 1.2 and is lies between 1.2 to 2.5 or 3 depending upon the type of the metallic reinforcement. If it is a metal strip, so you can interpolate and can calculate this. If it is a metal bar or mat welded work grid, so you can also calculate what will be the stress ratio, and here it has been shown that how the variation of stress ratio with the depth. So, you look at this variation after 6 meter, it is constant in case of the inextensible reinforcement. So, this is not applicable in case of the strip for the geosynthetics material. For the geosynthetics material, and this Kr by Kr will be equal to the 1, that means Kr will be the K of Ar. So, you have to be select this stress ratio Kr by Kar based on the type of the reinforcing material, type of the inextensible reinforcing material. As I mentioned earlier, that if it is a horizontal backfill surface, you have to calculate what will be the active earth pressure coefficient, and then active earth pressure coefficient can be calculated by Ka is equal to tan square 45 degree plus pi by 2. When the backfill is inclined at an angle beta, then you have to adopt this equation, that is Ka is equal to cos beta bracket cos beta minus roots of cos square beta minus cos square pi divided by cos beta plus roots of cos square beta minus cos square pi bracket complete. While where pi is the internal friction angle of the soil and beta is the backflow which is inclined at an angle of the beta. So, you have to remember that if it is a horizontal backfill surface, so you adopt this K equation is tan square 45 degree plus pi by 2. If this is an inclined with an angle beta, so you can adopt this second equation, that is K is equal to cos beta, that is cos beta minus root over cos square beta minus cos square pi, cos beta plus root over cos square beta minus cos square pi. So, you remember that depending upon that whether it is a horizontal backfill surface or it is an inclined surface. Now, we calculate the maximum mobilized tensile force in the reinforcement. At any depth Z, vertical stress sigma V is equal to gamma of Z. So, if you consider that this is the ground surface and at any depth, so you can calculate that what will be the sigma of Z, and also you can calculate that what will be the horizontal stresses. So, here that sigma, if it is a sigma of V, that means if this depth is equal to the Z, so you can write that sigma V is equal to gamma into Z, and gamma is the unit weight of the soil, and the horizontal stress is sigma of H. So, sigma of H will be equal to Kr into sigma of V. So, this Kr can be interpolated from the figure, this figure Kr by Kar. From this you can interpolate and can determine that what will be the stress ratio. That means, if you know that Kr by Kr is equal to, let us say 1.7, so it will be known to you. So, here how we are calculating this Kr value. So, maximum horizontal mobilized tensile force which is designated at T of maximum, and this maximum horizontal force in the reinforcement is rely on this tributary area. If that area is equal to A of T and this is sigma of H, so T max, maximum mobilized tensile force in the reinforcement in the tributary area will be equal to AT into sigma H, then sigma H is equal to Kr into sigma V. So, A of T is the tributary area which can be taken as twice the panel width. So, from this you can calculate that what will be the maximum mobilized tensile force. Now, this at any point you can see here that if it is the sigma of V and this is the sigma of H, that is Kr into sigma V, and this is the T of maximum here, the tensile force acting here, T of maximum. This is the mobilization of maximum tensile force in the reinforcement, and this is the reinforcement. So, here that some explanation is given for the tributary area, that means reinforcement of our tributary area. This is the reinforcement and this is the panel. You can see this is one panel, this is one panel, this is half of the panel, this is bottom of the panel. This panel is length and and the height is almost 1.5 meter, and this is the ace of V, this is the ace of V, that is the spacing, and the tributary area will be equal to 2 into panel width, 2 into panel width, and this is the horizontal spacing between the reinforcement, that is ace of H, and this is the vertical spacing between the reinforcement, it will be ace of B. So, here it has been focused on the reinforcement of a tributary area, that means twice the panel width. Here also same in case of the metallic reinforcement, you can see what is this bilinear type of the failure surface, and this also the vertical spacing which is lied between 0.2 meter to 1 meter. So, you can change that vertical spacing, also you can change the horizontal spacing which is lies between 0.8 to 1 meter. So, you can change the spacing and you can optimize and can design accordingly. And here this is the length of the reinforcement, if it is length of the reinforcement is L, and this is the embedded length or the bond length LE, and this is the LA is equal to active zone length. So, you can calculate this what will be the total length, and this failure making at an angle of 45 degree plus theta by 2. Now, considering the factor of safety against pull out failure, it should be factor of safety against pull out will be greater than equal to 1.5. So, pull out resistance PR would be greater than equal to 1.5 into T of maximum. If the minimum number of the reinforcement required in the tributary area to achieve the pull out resistance is equal to N, then N will be equal to PR divided by 2 into B into F star into LE into sigma V dash. So, what sigma V dash is vertical pressure at this level ignoring the any surcharge pressure, and B is the width of the reinforcement strip, and LE is the embedment length of the reinforcement, that is L minus LA, or L is equal to total length of the reinforcement, or LA is equal to length of the reinforcement in the active zone. So, it is like this. If I draw a failure line, if it is the wall, and if this is the reinforcement, this is the reinforcement, and you can draw a failure line like this, and let us say failure line like this, and this is the embedded length L, and this length is equal to L of A, and this total length is equal to L. So, L is equal to LE plus LA, this is LE plus L of A. So, we require what should be the value of LE. So, this will be LE will be equal to L minus LA. If you know that what will be the height of the reinforced soil wall, and L is generally considered for the design is 0.7 times of the H. So, you know the what will be the height. So, you can calculate what is L, and from here if you know the angle, so you can calculate what will be this length, then you can calculate what will be the embedded length. So, we can calculate this embedment length from this. Now, this smooth, if it is a smooth strip, this F star will be equal to tan of delta, that is regardless of the depth. What delta is equal to friction angle between the soil and the reinforcement in the reinforced zone. and if it is a rebate strip, F star will be equal to 1.2 plus log of Cu, that is 2 is maximum at Z is equal to 0, is equal to tan pi r when Z is greater than is equal to 6 meter. What Cu is the coefficient of uniformity and pi r is angle of internal friction of reinforced backfill. So, if we look this figure, this is the rib strip and this figure is variation of friction factor with the depth. This is friction factor with the depth. So, this is tan pi r, this is tan delta, pi r is internal friction angle of soil in the reinforced zone and delta is friction angle between the soil and the reinforcement, and this is the friction factor. You can see friction factor which is denoted as F of star. This friction factor value depend upon the type of the reinforcing element. If it is a smooth strip, F star is equal to tan delta and regardless of depth, and if it is a rib strip, F star will be equal to 1 plus 1.2 plus log of Cu or 2 maximum value. What Cu is the coefficient of uniformity, and if you know that what will be the coefficient of uniformity of that soil, so you can directly determine what will be the F star for rib strip, and this I say that maximum value is to at a depth of when Z is equal to 0, and then the F star will be equal to tan pi r when Z is greater than or equal to the 6 meter. You can see here when this is the 6 meter, when it will lead to this 6 meter greater than or equal to the 6 meter. So, we have shown these two figure. One is in terms of the lateral stress, that is Kr, Kr, what ratio you should take into consideration into the design for the inextensible reinforcement, and the earlier slide shows that what should be the friction factor that depend upon the type of the inextensible reinforcement, and is goes on up to the 6 meter, and after that almost this constant. So, also we conclude that how the F star factor also depend upon the coefficient of uniformity of the soil. If you know the coefficient of uniformity of the soil, then also you can calculate this friction factor, and this also when you can calculate at a depth of Z is equal to 0, at a depth of Z is equal to 6 meter and above. This slide shows the cross section of the metallic reinforcement. So, this is the, you know that in case of the metallic reinforcement, failure pattern bilinear failure, and this is the height of the wall, and this is the spacing between the two reinforcement SB, this is the length of the reinforcement, this is a measurement LE, and this is LA, and this distance is about 0.3 times the height of the wall. Now, because we are using the metallic strip reinforcement, and that was the reason that we should also study that what will be the effect of the moisture, what will be the corrosion effect of the reinforcing material, and what should be the longevity and durability of this material. So, we should know that how many years the reinforced soil structure can last, whether it is 75 years, 120 years, like this. We have to be very careful about the corrosion effect of the reinforcing material. This is one of the most important point here, because the most of the cases we use the metallic reinforcement or galvanized metallic reinforcement, which will come in contact with the moisture content or water content, and then reinforcing material may deteriorate it. There will be a corrosion effect, and then there is a possibility for the collapse of the structure. So we will see that how the tensile stress of the metallic strip at the design life. So there is a specification for the Federal Highway Administration FHWA 1990, and then you can calculate that what will be the thickness loss per year. So it has observed that zinc loss is equal to 0.015 millimeter per year first 2 years, and then zinc loss is equal to 0.004 millimeter per year thereafter. Now steel loss 0.012 millimeter per year per site thereafter. So we have to check that what will be the total thickness loss during the design life, that means T loss, and remain thickness at the end of the design life is equal to T remain. The remain cross section after the design life of 75 years, if the cross section remain is designated at S of C, A of C. So A of C will be equal to what will be the thickness remain and the B. So you can calculate the what should be the remain cross section after design life of 75 years. Now because it is a metallic strip reinforcement or inextensible reinforcement, and it is universally well known about the yield stress of the steel, and we know that ultimate yield stress of the steel, which can be designated as F of Y, and generally if we consider the 60 grade of steel, so Fy will be equal to 413.7 MPa, and we have to consider for the allowable ultimate yield stress of the steel, if it is designated F allowable, so F allowable will be equal to 0.55 F of Y. So tensile stress Fs in each strip can be calculated with this equation, that is Fs is equal to T of maximum divided by N into AC, and this value should be less than the F of allowable value. If it is less, then it is okay. Jewell 1991 reported the polymer material, that is extensible reinforcement, mobilized a relatively high strain due to the extensibility of the reinforcement. Therefore, the critical shearing resistance angle of the soil is recommended rather than the peak angle of soil in the design. I will now give you some example, design example of inextensible steel reinforcement for the retaining wall. So let us consider that wall geometry of the and the external loading. So height of the wall is about 9 meter, and traffic surges Q is equal to 10 kilopascal. Angle of internal friction pi r is equal to 30 degree, and interaction coefficient between foundation soil and the reinforcement Ci is equal to 1. Allowable bearing capacity of the soil is 300 kilopascal. The engineering properties of the retained and the reinforced backfill, that is angle of internal friction of retained fill is 30 degree, and unit weight of retained fill gamma T is 19 kilonewton per meter cube. For angle of internal friction of reinforced backfill, pi r is equal to 32 degree, and unit weight of the reinforced backfill gamma r is equal to 19 kilonewton per meter cube. These are the data is given for a inextensible retaining wall. It is given that what will be the wall geometry, what will be the properties of the foundation. That means we should know what will be the properties of the foundation is very important, and we should know what will be the engineering property of the retained and reinforced backfill. So if I can show like this is, if this is the foundation soil, this is the foundation soil. So you should know that what will be the properties of the foundation soil. You should know that what will be the properties of the retained soil. You should know the what will be the height. These are the property is given for the design for the reinforced soil wall. Now when you will design this reinforced soil wall, then you require some factor of safety. So you require for the design for the external stability, you require for the design for internal stability. So you have to check up what will be the factor of safety against the sliding, and then factor of safety against sliding should be 1.5. What should be the maximum foundation pressure, and that should be less than equal to allowable bearing capacity. And at the same time, due to overturning there is a possibility for the failure. So you have to consider the eccentricity, that measure of earth pressure distribution. So eccentricity E is given is equal to less than equal to L by 6, and you have to check up the global stability which should be greater than equal to 1.3, and for the internal stability you have to check what will be the factor of safety for pull out resistance, that should be greater than equal to 1.5, and allowable stress, because for this is a inextensible reinforcement which will be equal to 0.55 f of y, and we consider the design life for the 75 years. So you have to check that what will be the design life, what will be the factor of safety for the external stability and as well as for the internal stability. And when you will design this metallic reinforced soil retaining wall, you have to choose the facing element. So there are different types of the facing element. I am just showing one cruciform facing element whose dimension is about 1.5 meter by 1.5 meter. Every 3.75 millimeter spacing or 750 or 3.75 like that spacing, you can connect the reinforcing material with the facing element. So we also have to check up that what will be the size of the panel. We can also check up the local stability of the panel and what will be the dimension of the panel. Let us say that dimension of the panel is 1.5 meter by 1.5 meter. Different manufacturers have their different types of the panel, but in case of the metallic reinforcement, majority use this cruciform of the panel, precast concrete panel, and also you should know what will be the metallic strip of the reinforcement, and each and every metallic strip of the reinforcement have a width. So, width be equal to 50 millimeter, thickness of the metallic strip reinforcement is 5 millimeter, including a zinc coating of 0.086 millimeter, and 60 gauge steel was used. Vertical spacing between the reinforcement SB we consider 0.75 meter. So, you can see this is one of the facing element in Cauchy shape form, and this is 1.5, and this is also 1.5 meter, and this reinforcement is connected with this facing element here, and this spacing is 7.75. So, this vertical spacing SB is 0.75. Then you have to place another panel here. Then you can see half of this panel is 0.375, another 0.375, that means spacing will be equal to 750. Like that you can construct this reinforced soil retaining wall. So, these are the some data which is given for the design of this kind of the wall. Now, we will give you the solution for this. When you design the metallic reinforced retaining wall, you have to assume that what will be the length of the reinforcement. I said that if the height of the reinforcement is h, and then the length of the reinforcement is 0.7 times of the h. So, for general purpose design of reinforced soil wall, so length you can consider is 0.7 times the height of the wall. So, first step, preliminary length for reinforced strip you have to consider L is equal to 0.7 h. You know that height of the reinforcement is 9 meter. So, length is equal to 0.7 of h, that means 0.7 into 9 is 6.3 meter. Step 2, we will move on to external stability. You know the coefficient of active earth pressure for the retained backfill, that is KAT. KAT is equal to tan square 45 degree minus pi t by 2, and pi t is given 30 degree. So, if you substitute this value KAT, you can calculate that tan square 45 minus 30 degree by 2 is equal to 0.33. Now, look here, this is the wall, the height of the wall is 9 meter, and there is a surcharge, that is W of Q, and this is the reinforced zone weight, which is designated as W of R, and gamma R is equal to the unit weight of the reinforced soil zone here, and this is the length of the reinforcement. Now, this reinforcement may fail due to the sliding. You can see that is why you need the resisting force, which is designated by F of R. So, when you will design this kind of the wall, you have to check what are the pressure inserted into this reinforced soil wall. So, this is the backfill here. So, here the forces acting on the reinforced soil wall is the what will be the soil pressure. So, soil pressure, you can see that triangular distribution, and this pressure forces which is acting at a height of h by 3, if h is the height of this reinforced soil wall. So, this horizontal forces for the soil pressure will act at a distance of h by 3 from the base of this soil. So, this is a triangular distribution, and due to the surcharge load, you can see this is the surcharge pressure that is uniformly distributed, and this is force is F of Q, which is acting at the middle height of the reinforced soil wall, that means h by 2 is h is the height of the reinforcement. So, you have to first consider whatever the forces is acting into the wall. The forces acting due to the soil pressure, forces acting due to the surcharge pressure. If suppose there is any live load, that also you have to take into consideration into the design. If there is a earthquake also in the seismic zone, that also you should consider into this design. But here in this example only we are considering the soil pressure and the surcharge pressure. So you have to check that what is the pressure is acting, what are the forces are acting on the retaining soil wall. As the reinforced soil wall, the rest on the foundation soil, here foundation soil. So foundation soil may be very poor, so you want to improve the foundation soil. If you wanted to improve the foundation soil, there are various systems we will cover during our geosynthetics mechanically stabilized reinforced soil wall, but we have to determine that what should be the stresses on the foundation soil. So we will adopt this Mayer of pressure distribution. So if L is the length and this is the vertical pressure is sigma V, and this distance is L minus twice E, E is eccentricity, and this distance will be twice E. So total length will be the LE. So when we will design for the what will be the factor of safety against the bearing capacity and the vertical forces which is acting upward, that length we should consider L minus 2E, and this is the Mayer of earth pressure distribution. For all cases I should recommend that you should follow up the Mayer of earth pressure distribution. So L minus 2E zone will be the active zone. So we have to check up for the factor of safety against the sliding. If this wall fell due to the sliding, you can see that wall may move and you are resisting with the force. So there is a possibility for fail for the sliding. So factor of safety sliding means the ratio of total resisting force without considering the surcharge here divided by total driving force FD. Total resisting force without considering the surcharge Fr is equal to WR Ci into 10 pi R. If you can look here that this is WR and this frictional forces is acting here. So this frictional forces is 10 of pi R. So this is Ci value is equal to here 1. So Ci is equal to 1, that is Fr will be equal to WR into tan of pi R, where pi R is equal to angle of internal friction for foundation soil, which we consider as 30 degree. So then we have to calculate what will be the weight of the reinforced soil zone. So we know that what will be the length of the reinforcement, we know that what will be the height of the reinforcement, we know that what will be the unit weight of the reinforced soil zone. So weight can be determined by the unit weight of the soil in the reinforced zone into length into height. So that is why we have calculated WR is equal to gamma R H into L, gamma R is equal to 19, height of the wall is 9 and L is equal to 0.7 times of height, that means 6.3. So you can calculate WR is equal to 1077.3 kilonewton per meter. So total resisting force Fr will be equal to WR Ci into 10 pi R, that is WR is equal to 1077.3, Ci is 1, 10 pi is 30 degree. So total resisting force will be 621.98 kilonewton per meter. So at the same time you know the resisting force, also you should know that what should be the driving force. So driving force also can be written as what should be the active pressure, force from the retained field and what will be the active pressure force due to the surcharge load. So, here this active earth pressure from the retained field is equal to half KAT gamma T into H square, half into KAT value is equal to 0.33 and gamma T is 19, H is equal to 9, this is 9 square. So, this FA, that means active earth pressure force from the retained field is 256.5 kilonewton per meter, and FQ is the active earth pressure force due to the surcharge, that is FQ is equal to Q into KT into H, because this is the surcharge pressure. So, 10 is the surcharge load and gamma KAT is 0.33 and H is equal to 9, it is equal to 30 kilonewton per meter. Hence, total driving force FD will be equal to 256.5, that is F of A plus FQ is equal to 30. So, total driving force will be summation of FA and FQ, that means 256.5 plus 30 will be equal to 286.5 kilonewton per meter. Now, we have to check that what will be the factor of safety against the sliding, that is the resisting force divided by driving force. So, resisting force which we have already calculated, that is Fr is equal to 621.98 divided by driving force is equal to 286.5 kilonewton per meter. So, this ratio is equal to 2.17 and we have to check that this factor of safety against sliding should be greater than equal to 1.5. So, if this factor of safety greater than equal to 1.5, that means it is okay, structure is in stable condition. With this I ended up this lecture. Thank you for listening.